rotation. And
okay, unfortunately, the yo-yo has mass, which makes it annoying. And it's got a radius, so that makes it even more annoying. Well, actually, once you got mass, you need a radius. I got tension in a string I'm pulling up with. Oh, this problem reminds me of a very nasty problem. It could be the same sort of problem. Solid cylinder, mass M and radius R is wound around a string around it. The person holding the spring pulls it up vertically, as shown above, such that the cylinder is suspended in midair for a brief interval at delta t. And the center of mass does not move. So the center of mass is not moving while I'm doing this. When I'm pulling up the rope, I manage to keep it in place. Does that make sense?
Yeah.
Okay, so there's a couple things that tells us, but tension string T and the rotational inertia around the cylinder is 1/2 the inertia. They're giving us the inertia, right?
Yeah.
As promised, usually they're going to give us the inertia. All right, so you can skip 23. Let's do 24. It was E? No. Oh, actually, yeah. I guess it would be E. Oh, that's funky.
It's like the tensions.
There's a net force, right? It's a net force. You'd have to be E, right? Because it's not moving. It's not going up. They're not going up or down, right?
Yeah.
Center mass is not moving. Perfect. That does tell us, by the way, my tension is going to be equal to my mg, correct?
Yeah.
Which might be handy and worth considering. Linear acceleration of the person's hand during the linear acceleration of the person's hand?
Yeah.
So that's going to be equal to the angular times the radius, correct?
Wait, why would it be?
The angular of this times the radius of it would be the acceleration of a point on the edge, which is going to be the acceleration of the string, agreed?
Yeah. So
okay, so I got to find angular acceleration, which means I'm going to go into the land of torque net equals the sum of all torques.
that would be inertia times angular acceleration.
So that would be inertia times angular acceleration equals now I got two forces on this. I got torque. I got tension times radius plus force of weight times radius.
And you have to do it by radius because it's angular.
Right, because it's torques. Torques is always where it's applied. It's important. If you can't go through the center mass, it does nothing. Which is my next point, anyways. How far is my radius from how far out from the point of rotation is this force applied? 0. So this is going to go away.
That's because the center of mass is in the center.
The center mass is in the center, right? And because the force of weight's applied at the center mass, weight does not cause things to rotate.
Yes.
Right? Unless you pin it somewhere, weight can't make it rotate, right?
Yeah. And the T.
So the T is going to move up. So T is a variable we have. Radius is a variable we have. I want to find angular acceleration, so I'm just going to go TR over, I assume this is perpendicular.
Yeah.
And then I is equal to 1/2 mr squared. So one of the r's just cancels out. So alpha becomes 2t over mr. So far, so good?
Yeah.
How do I turn angular acceleration into linear acceleration? Multiply by the rate. R equals linear acceleration. I had to multiply by R, which cancels that out. So I get 2t. Uh-oh.
Okay, yeah.
That's not one of the choices, though.
Well, you have tension equals mg.
Oh! 2g?
And then you multiply by
2g done.
Yeah.
B. Thank you for that last bit, because I was starting to panic. Inside my stomach was starting to churn like, uh-oh. Done something completely wrong. Yes, sir. 21. 21. Which one was this, by the way? This was
24.
24. 24. Now I'm going to do 21. All right, talk to you about 21. What's going on there?
Someone standing on a raft.
Whoa! Center of mass. Here's the man. Now here's the center of the raft, and there's a distance d to the center of mass, right? Why is the center of mass off the center of the raft? because he's standing on one end. We're calling him part of the system, right? Person standing at the end of the uniform raft length L, floating motionless on the water, shown above. Center of mass of the person raft system is a distance d from the center of the raft. The person then walks to the other end of the raft. If friction between the raft and the water is negligible, how far was the raft moved relative to the water? Well, the center of mass is not going to move, right? This point's not going to move.
So
Agreed?
that's the other side of it.
So the raft, when he gets to this side, when he gets to this side, and is on the raft, the center of mass can't move, right? So how far is the raft? Where's the center of the raft going to be?
Oh,
It's going to be on the other side, right? And so if it starts D here and goes that way, it's going to move a total distance of 2D. I got E. Always the right answer. Again, you're skipping 22 because you see something like that on the AP test, they take, just move on. And you got a little time at the end of the test. We'll talk a little bit more how to do that in chapter 7 in calculus. This is not a great physics problem. First, the takes to turn it, correct? Current force going to end up turning it. So two blocks of mass 1 and M2 are connected over mass pulleys of our wheel. Shown above. M1, T1, T2, M2. Because this thing has mass, there's no guarantee that these two tensions are the same anymore, right? Because some of the tensions are going to get used turning the darn wheel. Okay. It goes angular acceleration, rotates clockwise. So it's going in and rotates clockwise. So it's got angular momentum and rotates that way. Angular acceleration, which of the following statements about T1 and T2 is correct? Okay, so T1 and T2 has to be the same. No. Why? Turn the wheel. In fact, T2 has, we now know T2 has to be bigger than T1, correct? All right. T1 equals T2. We're moving on. T1 has to be greater than, nope, that's not it. Nope. T2 has to be greater than T1 because the unbalanced clockwise torque is needed to generate the wheel, right? That's got to be it. Unless I'm missing something, which I don't think I am. No. Orange 33. Orange 33. The figure above shows satellites S2 and S3 are to equal mass traveling around the Earth in these circles of radii R2 and 2 of the REs. Okay, good. REs radius of the Earth. How do the kinetic energy, the angular momentum, and the angular of each apply? So, which one do you want to solve first? Kinetic energies. Kinetic energy. So we know, what do we know about something in a circular orbit? What? Oh, yeah, it'd be the same for every spot in orbit. That is true. That is absolutely true. What do we talk about circular orbit? One thing should leap immediately to your head. It has nothing to do with energy. Force centripetal is divided by force of gravity. mv squared over r equals g m1 m2 over r. Those of equal mass. Right. Equal mass.
Was it over r squared? Or
r squared, yes. Sorry. So that cancels out with one of those. And look what I got here. I essentially have kinetic energy. Right? Yeah. I put a 1/2 over here. And the kinetic energy current is 1/2 GMM over R. So how do these kinetic energies relate to each other? Well, these two terms are the same. The g's the same. 1/2 is the same. So what's the only thing that's different between the two?
The radius.
Radius. So one of them is going to have 1/3 radius, and the other is going to have 1/2. Right? So one's going to have half.
Well, the greater radius would be have less.
Have less kinetic energy.
And then for momentum,
Okay? So then momentum, we're going to go angular, is it linear momentum or angular? Angular momentum. Angular momentum is L equals I omega, which we write as mvr, correct? Now this is going to be a little trickier because we have this situation here, right? Because our velocities are not going to be clean. They're going to be really icky, in fact. So we throw the next one. So the mass is the same, so that doesn't matter.
yeah.
One of them is going to have a 3R, one's going to have a 2R. Agreed?
Yeah.
Oh, wait. This is interesting. Oh, okay. Well, first of all, the R's are going to cancel out, correct? If I put them back again, oh, it's putting this kinetic energy. I don't want to do that. Never mind. I lied. Don't do that. That's bad. Right?
Yeah.
So we know which one has a higher velocity. The one's 2 out, yeah? And so if we square root this, essentially what we have to do, so let's go back and go 1/2 mv squared, right? I'll get rid of the 1/2 because I don't want those. Oh, wait, there's a 1/2 out front when I started, so that's not the right thing to do. Never mind, leave that there. And then the m's cancel out, so I got a square root of gm over r. Agreed?
Yeah.
So one of them is going to be 3r on the bottom square root. The other is going to be 2r on the bottom square root. Agreed?
Yes.
Okay, so if I assume everything else is the same, I got blah 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 for m, right? That's the same. Agreed?
Yeah.
My velocity is going to be what?
2.
It's going to be blah blah blah, same for both. But on one of them, I'm going to have a square root of 2r on the bottom. The other one, I'm going to have a square root of 3r on the bottom, right?
Yeah.
And then what happens with radius?
That would be 2r and 3r.
Right? So if I simplify this, I get blah, 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 square root of 2r, and one of them is blah, 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 square root of 3r. So the 3r one's going to be bigger. So the farther out, it's going to have bigger angular momentum, but less kinetic energy. So now I got to figure out less for S3. So S3 has less kinetic energy and more angular momentum. All right. Yeah, I'm going to look at 33. 33, the correct answer. Oh, so much answer is. Hold on. 33, the correct answer was in fact A. And you know what percent of people got that right? 21%.
Yeah.
5 multiple guess, 21% got that right. Statistically speaking,
Probably would not have gotten it. The answer was.
Statistically speaking, that's one of the ones you should pass on.